right, so now we're going to start chapter 4, which deals with the shapes of molecular compounds, and then we'll start getting into the organic chemistry section for this term. So an outline for this section is that we're going to review drawing some Lewis structures, and then we're going to focus on the shapes of molecules, because as we'll get into the organic chemistry, we're going to see that the shape of the molecules is very important for helping determine the function of the molecules. This is especially true for biochemical molecules like proteins and DNA. So by the end of this section, you should be able to understand how molecular compounds are represented, so looking at our Lewis structures and formulas for drawing our molecules. You should be able to tell what the influence of the valence shell electrons are going to have on the molecular shape of the molecule. And then we'll review again when our bonds and our molecules have polarity to them. So being able to use the electronegativity periodic table and the molecular geometry to help predict the bond and the molecular polarity. So who cares about the molecular shape anyway? Well, the shape of a molecule, again, is going to play a very important role in determining its properties or its function. So properties such as the smell of a molecule, taste of a molecule, or in the case of medicine, the targeting of drugs are all the result of the molecular shape. So understanding and studying how the molecular shape forms is a very important process. So to help us understand the molecular geometries of organic molecules, we're going to study something that's called VSEPR or VESPR. So our Lewis dot structure to writing molecules provided some insight into the molecular structure in terms of bonding. But we really didn't look at geometry last term, so we're going to focus a little bit on the geometry of the molecules. So we have two types of electron pairs that we're going to be interested in. We're going to be interested in bonding pairs. So that's when two atoms come together and they're going to share the electrons in a bonded pair. But we also note that some atoms have lone electron pairs as well, like our nitrogen and our oxygen, for example. So both of these types of electron pairs will affect the geometry or the shape of the molecule. So VESPR stands for valence shell electron pair repulsion. What this theory suggests is that the three-dimensional structure of a molecule is determined by minimizing the repulsion of the electron pairs. Because electrons are all negatively charged, they're going to repulse one another, and so they want to be as far apart as possible. And that's really what's going to help determine the three-dimensional structure of the molecule. So remember that molecules can be represented in many ways, and we've already seen several. We can have the molecular or the chemical formula. So for carbon dioxide, this would be represented as CO2. But we can also draw this molecule in different formats. We can use the structural formula, where you're actually drawing out the bonds, or you can have the Lewis structure, which gives you a two-dimensional representation of the molecule. And the difference between the structural formula and the Lewis structure is that the lone pair of electrons are also included in the diagram. So you can see in this molecule, all of the carbon's electrons in its valence shell are being shared with the oxygens in these four bonds. The oxygens each have two lone pairs of electrons that are also associated with them, and they're indicated by the dots. So the shapes of our molecules then can be predicted by noting how many bonds and electron pairs surround the individual atoms and applying what's called the valence shell electron pair repulsion model. So the basic idea of the VESPR model is that you have negatively charged clouds of electrons that are either in bonded pairs or in lone pairs, and that they repel each other and they keep as far apart as possible. So that's really the entire theory. So if we take a molecule like methane, so we've got carbon bonded to 4 hydrogens, you might initially think that this might be the best geometry for getting those hydrogens as far apart as possible from one another. So it's actually the electrons that are shared between them that want to be the farthest apart possible. We know based on this molecule, if it's flat like this, the angle between each of the bonds is going to be 90 degrees. However, If we look at this configuration here, where we actually use three-dimensional space a little better and form a tetrahedral structure, we can see that the bond angles between each of the bonds is about 109.5 degrees. So this is quite a bit farther than the 90 degrees that we could get by having these extending off all in a planar direction. So this is actually the conformation that provides the greatest bond distance from one another. So it gets the electrons as far apart as possible. So when we're thinking about the geometrical shapes, 5 major shapes are going to pop out at us. We can have linear, which is going to separate the electron pairs by 180 degrees. That's probably as far apart as possible. We have 120 degrees. This would be trigonal planar. So these are all in the same plane, kind of like we saw with the methane here just a minute ago. It's all in one plane, but there's only 3 bonds, so they're 120 degrees apart. We already saw the tetrahedral example with the methane molecule, where you've got kind of this pyramid type shape, and each of the bonds is separated by 109.5 degrees. You can also have trigonal bipyramidal, and so you've got 120 degrees in this planar section here, and then each bond is going to be 90 degrees apart in the upper quadrant. And then you can also have an octahedral structure in which there's 90 degrees in all directions. And so you can see you've got 6 components bonded in this structure. This structure, you've got 5 components bonded to a center atom, 4 components bonded to a center atom, 3, and then 2. So molecules are going to adopt a geometry or shape that minimizes the electron-electron repulsions, and this occurs when the electron pairs are as far apart as possible. So when we're considering the shape of the electrons, we need to consider both the bonding and the lone pairs to help minimize the repulsion. So our example of methane is a good one to start with. So we can see that our carbon, our center atom, which is what we're looking at the molecular geometry of, does not have any lone pairs. It only has bonded pairs, right? So each of the electrons from the carbon is sharing with each of these hydrogens. So this would be the Lewis structure for methane. This would be the geometrical shape that the carbon would take, is the tetrahedral shape. So we would say that the VSEPR molecular geometry shape is tetrahedral. So now let's take another example. We've got NH3. Let's draw the Lewis structure for this molecule. So we can see we've got 3 bonds going to the hydrogens, and you can see nitrogen also has 1 lone pair as well. So let's see how this is going to affect the shape. So we still have to take into account that the nitrogen has this tetrahedral shape. One of the bonds is going to be the lone pair electrons. So this actually will push down. It's kind of like a big basketball sitting on top of here. And it will push down on the other bonds so that they're not planar. They're not just coming off of the center, but they have a pyramid type shape to them. So what you actually physically see are the hydrogens that are extending from it take on this pyramid shape. So the VSEPR structure for this guy, the molecular geometry is pyramidal, but the electron geometry is still tetrahedral in shape. So we've got the full electron geometry. The molecular geometry only describes the bonded electrons and where they're going to and what that shape looks like.